Okay, so I realize I'm the last presentation before lunch, so some hardcore heat transfer to get us going here. Let me first acknowledge my co-authors, Chao Zhang, Morgan Bruns, and Salah Benko-Ricci. I want to preface this by saying that I don't really consider myself a pyrolysis expert. I learned a lot from Morgan and working on this this sort of side project, and I think we're just kind of at a stage where it's hopefully in proof of concept, and we're kind of trying to see where this takes us. This really kind of all started when Chao came to me, and they were trying to model the commissioning tests that are taking place at the large fire lab that you'll see tomorrow afternoon. And he wanted a better estimation of the surface temperature on these I-beams that he could feed into his structural analysis codes. So he said, okay, can we do three-dimensional heat transfer in FDS? I said, no, but I don't know that it would be that hard to implement, so let's give it a try. So that's where this kind of all got started. We then thought, okay, well, maybe there's also some application to maybe downward and lateral flame spread type calculations, and as we move toward more complicated geometries in FDS, you can imagine that also, and maybe more sophisticated pyrolysis models that we want to be able to deal with three-dimensional heat transfer. I've also seen some interesting talks, for example, by Guillermo Rain's group talking about peat fires and smoldering combustion, and he shows some interesting phenomena in these large-scale wildland peat fires where there's multi-dimensional transport and effects that lead to these overhangs that eventually collapse and can generate these massive sinkholes that are a problem for firefighters. There's actually been some interesting previous work that's gone into this area. I'm not the first one to try to implement three-dimensional heat transfer into FDS. Some very nice work was done in 2009, 2010 by Andreas Fischer, and also there's some ongoing work at Braunschweig by Matthias Simon and their group. I've been in email contact with these groups, and unfortunately it's just been sort of difficult to actually get these codes ported over and merged into our main branch. But this is, like, as I say, this is very ongoing work, and if somehow that materializes in the future with someone that wants to help maintain this code, we're certainly open to this. For completeness, I should also, of course, mention that GPyro has three-dimensional capabilities, and Stas's code Thermakin at University of Maryland has multi-dimensional capabilities. And I believe Chris has even ported GPyro to work with FDS6. But again, as we've moved along in this project in sort of baby steps that have led us where we are, it's been nice to it's been a little bit of an educational process also for me to learn about pyrolysis, and it's kind of been nice to have a bit of control over the source code. So anyway, we'll just kind of see where this goes. One of the sort of things that we built into the code from the start, and which kind of one of the reasons we wanted to sort of, the idea that we had, or that was the seed for doing this, was to actually use the same temperature array that we use for the gas phase that's usually just simply masked by the solid obstructions. So what I'm going to show here is a little video of this I-beam case. It's sped up quite a bit, but we have now the capability of looking. You'll see this I-beam starts to heat up after a couple of minutes. And you're looking through a slice of temperature down through the center of the I-beam. So that's one thing, is that right straight away by using this temperature array, we have access to the slice files and device file output that's sort of native to FDS. So nothing has to change in PyroSim, nothing has to change in sort of anything else. We felt like that was nice. The other thing that we built in straight away was you see these lines here across, these are mesh interfaces in this simulation. So parallel capabilities are also built in straight away because the temperature array is a data structure that lives on a mesh, and so that the MPI exchanges there are handled automatically. Whoops. Okay, so the only equation slide really, so we're solving a temperature heat equation. So this says that the material derivative is proportional to the divergence of the heat flux, and we're going to have to talk about some issues related to deformation of the solid, and then we also have a mass transport equation. I realized after sending this to Brian that actually, strictly speaking, the way I've written these equations is not correct. There should be a gasification term here, but I also point out that a lot of the times the way you see these pyrolysis equations written down is also not correct. You'll just see a partial derivative here, and that, strictly speaking, isn't true. And I'm not sure that I've actually seen the correct equations written down for fully three-dimensional heat transfer and pyrolysis with multi-phase flow. So if this were, if I'd written a more complicated expression with multi-phase down, this would be correct. But since there's a gasification term I'm missing here, if I'm just considering the solid phase. However, the main point in writing this material derivative is I want to make the point, drive home the point that we have deformation effects that we need to deal with. It's not easy to handle those on a Cartesian grid, as we'll see in a second. Okay, so if you've spent any time dealing with solving conservation laws in a finite volume type method, this is what you usually deal with. Okay, where the flux of heat across between two cells is governed by, in the solid, Fourier's law, where you've got the thermal conductivity and you have a temperature gradient, and we have two values of temperature in two different cells, and what we're interested in is computing the flux at the face between these two cells, and these two cells have some volume. Here I'm representing by a delta X for each individual cell, and I'm going to consider that these cells may be of different size. Okay, so the very simple way to approximate the heat flux at this boundary is with a central difference that I'm going to show here. Here again, I'm accounting for the size of the cell. Okay, so what you may be more interested in, if you're a user of FDS, okay, well, now how do I implement this into my input file? So here what I'm going to show is a simple obstruction that I've made block 1 by 1 by 1. Now, usually the way the solid pyrolysis and heat transfer works in FDS is you put, you say something like on a surf line you would give a thickness, and then that's how you invoke the conduction model. So in an obstruction now, which is made up of several Cartesian cells in FDS, what we want to do is you just want to go in and you say HT3D is equal to true, okay, and this will invoke the 3D heat transfer model. Okay. Again, I'm taking this example from a case where I'm just doing heat transfer. I'm not doing pyrolysis yet. So my object maybe is to just do heat transfer in like a steel column or something like that. So normally in FDS you would apply your material properties to a surface. Okay. In the solid phase, the way the 1D solid phase model works, I feel like a more natural, when we started this, a more natural way to do this for 3D heat transfer is to say, okay, well, this obstruction, okay, is a solid, and it has material. It has a material. Okay, it may also have different boundary conditions, but the obstruction itself, the solid, is made up of a material. So you can now have a material line on the ops line. This is if you're only doing the heat transfer at the moment. I'll get into dealing with pyrolysis in a second. Okay, so and then the most general way to think about the boundary conditions on this solid is this surf ID 6, right? So you're supplying the surf IDs for each face of the solid, and so here I have an example where I have a cold face at 20 degrees, a hot face at 500 degrees. On the back side you can't see, I have adiabatic faces. Okay, you just do this like you normally would, specify a surf line, and then, okay, so then here's the key, boundary condition, if you will, that will make all this kind of go together with the solid phase, is that I can have a surface where there's two-way coupling between the solid and the gas phase. And to have such a boundary condition, you set HT3D equal true on that surf. Okay. So let's look at a quick example. This is something that Chao Zhang put together. So, of course, this is not an endorsement of ANSYS by NIST, but okay, he used ANSYS, which is a finite element code. And what he did is, this is just steel. I believe this is about 10 centimeters or something across here. He's got a hot patch that he holds at 800 degrees. On this face, and I think the case runs for something like an hour, okay, 3,600 seconds. With the same grid resolution, these are hexahedral finite elements with the same grid resolutions in a finite volume code. And within FDS, these are like 1 millimeter cells. So here I've got like 10 millimeter cells across the web. Then you get. I have also in the verification guide I have a more quantitative comparison between these two. But suffice to say, okay, so this verification is working. But it also highlights kind of a key limitation that we have at present with the model. Okay, I am resolving this solid. Okay, in order to get the temperature, time history right in this solid, I actually have to have the same amount of mass. Okay, here in the solid. Remember, in this case, it's to get an accurate solution. Even this is 10 centimeter. This is 10 cells across the web. Obviously, in practice, this is probably not like feasible, okay, for in the future. But we have plans to fix this. But we're sort of getting, we're getting our feet off the ground just with the multidimensional aspects of this at the moment. Okay, a similar case, we stole this idea from Chris Lautenberger's paper. But this is a solution from Karsla and Jaeger where you have a prescribed heat source inside of a sphere and a constant temperature boundary condition on the outside, and then you let this progress in time, and there's an analytical solution for this. Okay, and so we're doing a decent job matching that analytical solution. The details of these are all in the verification guide if you're interested. Okay, so now I want to switch over to talk about pyrolysis. And to get going on talking about pyrolysis, I want to first give a couple of definitions. First, what is the material density? So this is a property of the material. It says if you take a small volume that the material occupies and you look at the amount of mass of that specific material alpha in that volume, then the material density is like a property of that material. Okay, so when the bulk density changes, okay, that's changing because usually a material like wood, for example, is converting over into char, okay, or as the bulk density goes down, usually that's because there's off-gassing, right? So of some, the solid is turning into a gas, and the total material solid here is just the summation of the individual materials. Now, this presents a lot of challenges for dealing with deformation in 3D. There's challenges dealing with deformation in 1D, okay? But sort of a lot of the ad hoc tricks that we play in 1D, they sort of seem natural to the 1D model. In 3D, these same tricks that we play in 1D look a lot more kludgy. Okay, in my opinion, but nevertheless, we've got, just to get something off the ground, I'm going to talk a little bit about the tricks that we're using for getting fluxes cell to cell in a material that's deforming, and also how we deal with changing volume in the overall material. We're basically going to use the burn away function that's sort of natural to FDS. Okay. So if you go back to the slide that I talked about, which was just to compute the heat flux across between two, I'll probably use this term Eulerian cell quite a bit out of habit, but what I mean is a grid cell in FDS, okay? So this is a control volume that we form, which is a cell in FDS. Okay, as this material is deforming, if it's shrinking, in this case, then the actual dimension that solid has is something less than if you maintain the same density, then that material has a smaller dimension. Okay, and so the effect that would have would be to, if you have two material points of temperature, if you're going to take the derivative of those material points, it would enhance the heat flux. You would get a higher heat flux because these points are closer together, right, as the material has been shrinking. So we need to deal with how do we consider the fact that these material points have gotten closer together. And the way we do that is that we keep track of a new value in the Cartesian grid that's the local ratio of the Eulerian cell volume, V cell. Okay, this is what you would normally think of as the cell volume in FDS, dx times dy times dz, okay, to the volume of the solid. Okay, the ratio of the volume of the solid to the volume of the cell. We call this phi. Okay, you work through the definitions that I showed previously. You can show that this volume ratio is just a function of these densities. Okay, the densities that you have that you're solving for in your pyrolysis model, that comes in here, and then the material density. Okay, now we're going to look at two sort of simplistic cases that are going to kind of get us going here. We're going to consider the case in which the material shrinks isotropically. Okay, so it shrinks the same in all directions. Okay, maybe it's heated evenly on all directions, and we're going to consider the case that's typical of sort of like, you know, slab gasification or a cone calorimeter test where the material is heated from one direction, and so it's only changing volume in one direction. Okay, and when we do that, you can, based just on the cell volume ratio, you can compute from the cell volume, you can compute what the new material volume is, the solid volume, right? So in 3 dimensions, D is 3, okay? And so what just happens is that when you multiply the cell volume times this parameter or this factor, then you get it to the point where, you know, dx tilde times dy tilde times dz tilde gives you the material volume, okay, in this isotropic case, and similarly in the unidirectional case. So how do we? So now, you know, how do we take that and move on in the code? So so we start off again with these Eulerian cells, these grid cells in FDS, and we have the densities and we have temperatures. Okay, so the first step is to, using the formula I showed on the previous slide, to compute some new volumes. Okay, based on the densities that we have from the pyrolysis model. Okay, and what you have conceptually is something like this. You have a smaller volume. But then when we go to compute the heat fluxes from the intercell heat fluxes, we imagine now, okay, in each direction, we pretend like those solid volumes have actually collapsed on top of one another, which is, in reality, that's how things are. Okay, this was Morgan's insight to figure out how to get this stuff to work. And actually, so now once we have these, you know, these little vectors here that represent the heat flux, a cool property of these finite volume methods is that you can simply take these and move back over to your original Eulerian grid, okay? And things are still actually conservative. And you can conserve energy and mass within this cell. You just need to know what the flux is, okay? And given that we're using an explicit time stepping method, this actually helps us quite a bit. We don't get sort of handicapped by these very small grid cells, which if you were explicitly keeping track of that, you'd have to deal with, or go to some kind of an implicit solver, which is what the 1D model does. Okay, so here's an example of PMMA slab gasification. We're going to compare the 1D model, shown here on the right, with the 3D model. It has like about a 50 kilowatts per meter squared heat flux on the top. And we have the grid resolution. This is set up to be almost an identical case, okay? So that the grid resolution, which you can't really visualize in the 1D model, is the same here. And what the 1D model is doing, of course, is it's shrinking from the bottom up as it's pyrolyzing. And in the 3D model, actually, we're going to be burning away as this goes on. Okay. So as this moves on, what you'll see, and I'm showing here a slice of the material density, Okay, so these are we added some outputs. Now there's some nice, outputs that you can put slices, devices. You can look at material densities within the cell. You can look at the cell volume ratio and so on. And so, okay, so what you're seeing here is that the mass loss rate, obviously from this plot between the 3D and the 1D code, compare very well. All these little blips that you see are the are where you're getting burn away. So let's kind of stop it right sort of in the middle here for a second and get an idea. So each time one of these cells burns away in the 3D, you get one of these little blips. And then in the 1D, of course, you don't see it, okay, but you're also seeing these little blips going on as well. So these are some of the issues that kind of aren't always obvious in the 1D solver unless you go kind of take a closer look at some of these outputs. The thickness of the material is also a natural output for 1D. In 3D, we have to integrate, right? We have to count the number of cells, multiply by its DZ, okay? To get this to look so smooth, what I do is even in these cells, I'm not only saying, DZ times, and counting this is DZ times the cell volume ratio, right? And so that's something that we have that we output. When you consider the cell volume ratio, then you get something that looks, is right on top of the 1D model. We wouldn't also be able to get this close to the 1D model if we weren't in fact also using the 1D kinetics model. Okay, so another thing that we did here, okay, that nobody else obviously has been able to do because we just did it, was to extract the kinetics submodel out of the 1D code, separate it from the 1D heat transfer, which has always been sort of like integrated into sort of like one routine, right? So Kevin went in, pulled these things apart, and the 3D model now calls the 1D, it calls the pyrolysis model, right? The kinetics for the pyrolysis model are just the kinetics for the pyrolysis model. So we're not in this situation where we've got a branch of the code, going off with its own kinetics model, and this branch of the code is going on with a different kinetics model, right? They're using the same version. And I'm out. What'd I do? Whoops. Okay, I'll sort of skip over some of this stuff. There's a way to do radiation that we're working on. In the thermally thick limit, you can use a conduction approximation of radiation. Simo and I have had some exchanges about if this thing actually gets off the ground, that we would go ahead and use the finite volume method for internal radiation, but that's not implemented yet. Here's a verification case for the thermally thick version. The other thing that we've implemented is this idea of using a gas transport equation to do off-gassing. So one of the problems that you run into in 3D that's not as natural as 1D is, the 1D model just takes any gas and just throws it out the wall cell that it's attached to. In 3D, once you get into these in-depth cells, the question becomes, okay, like, well, which wall cell should you send the gas to? And you can try to come up with some ad hoc rules, but sort of a more natural way to do it is to just, use physics to some degree. Here we're going to use a simple diffusion model. This also has a lot of limitations. I mean, the real physics going on here is much more complicated. Porous media kind of approach. If you look at like Chris Lautenberger's paper, he has a lot of details about how he does this. For the moment, for us, we're just considering it as a simplified way to give a more plausible approach for where to send these off gas. Now we have both. We can do these both ways. We can also just send the gases to like up, for example. So you have the power to go in and say, okay, send the I'm doing a slab gasification and I want all the gases to go in the vertical Z direction. So you can say that, or you can say, and you should maybe be consistent with your model. If I'm using the isotropic model, then you would probably want the gases to sort of like isotropically expand. So in the top version here, again, comparing the 3D and 1D models, here we're just sending the gases to the nearest available wall cell, and on the bottom we're using the mass transport routine. what you'll see here is you see cases where, okay, this is burn rate. You don't see any burn rate on these cells because it's happening on cells that aren't facing you. Okay, whereas in the mass transport version, just like in 1D, you actually get mass that's going out isotropically based on the diffusion equation. The other thing that you'll notice here, if you look at the mass, the cumulative mass lost from these objects, is that the 1D model burns away faster than the 3D model. So this should be sort of intuitively what happens is the 1D model, of course, is gridded up to a much finer grid resolution than these 3D cases are. Okay, so let's just kind of look at these cases here for a second. I mean, this is only 4 grid cells across in each of these cubes. So it's actually kind of neat, and I'm going to show in the next slide how we do this, that we get anything close to the mass loss rates that you're getting in the 1D model. Okay, so here's how this sort of works. So in the 1D model, there's the grid resolution gets set for you automatically based on a stability kind of argument. Well, this is like the von Neumann number for thermal diffusivity, thermal penetration depth if you have a time scale of 1. Okay, so this is how this cell dimension is set. And of course you can change this with cell size factor or what have you. But if you have a Cartesian cell like this, then if I take the wall temperature minus the cell temperature, then I get sort of a smeared out. I don't have the resolution to get the high thermal gradient at the surface. But we play a little bit of a trick here in that when we're computing this wall temperature, okay, and implicitly the heat flux into this solid, we go ahead and use this value of delta, okay, in this approximation, and this is what gives us a reasonable value for the heat flux at the surface. I'll point out that the previous verification test was only testing mass conservation, so the actual result is not like an analytical result for the 1D model either. But what this reminds me of doing something like this is a bit like the way we treat stresses and heat transfer in the gas phase, right? We're not resolving the viscous sublayer in the gas phase either. So we have some kind of a submodel, in this case internal to the solid, to get the correct thermal flux without explicitly resolving the gradients there, which would obviously be prohibitively expensive. Okay, so just to wrap up, like I said, this is a work in progress. We've written it up in the guides. It's in beta testing. If anybody, has use for this, I would love to talk to you, and I can try to help you over any hurdles you have in getting it set up. We'd love to hear back to see how it's working. I realize that this issue of having to resolve everything in the solid right now is probably prohibitive for real life problems, but one of the things that we're trying to work on is to make this work for thin obstructions, and whether we can do this by coupling it to the 1D model, use 1D model in the normal direction, and then the multi-dimensional model in the lateral directions is kind of what we have in mind. We'll see if we can get that worked. I've tried it once and it wasn't as easy as I thought it'd be, but that's where we are. And I'll take any questions you have now.
Thanks, Randy. Do we have some questions?
A physicist asking me questions, that's going to be tough.
Yeah, thank you, Randy. No, just I don't know if it's already answered in the validation guide, because I haven't looked at this. But you compare this 3D over 1D pyrolysis model. Did you go and compare it to the experiment as well? And I'm thinking of an experiment where you can really see the advantage of having a 3D pyrolysis, because there are some experiments where
the short answer is no. We're working on it. I mean, the closest we have are these the validation cases, like the FAA polymers cases, where we've got the PMMA slab, and we've done that case. there's not really three-dimensional effects there to worry about. So, and but before the reason we haven't really charged on with that is because even just to get that FAA polymers case for PMMA right, you've got to deal with this internal radiation. Otherwise, you have errors of 20%, 30%, and so anyway, that's where things stand. We are looking for sort of tractable three-dimensional problems. The trouble is that these problems that really need 3D are actually pretty hard. So,
Thanks.
yeah.
So using the 1D heat transfer model can sometimes increase the computational costs a lot in comparison if you only use inert or adiabatic surfaces. What's the computational cost of using the 3D model now? Do you have an idea of
It's cheaper.
magnitude?
I mean, it depends on the problem. I mean, if you don't need to do the heat conduction, then don't do it. Right? That's the cheapest thing to do. If you need the heat conduction, then you making it adiabatic doesn't help you, right? So, yeah. I mean, the idea is that this I think has promise. Okay, this idea of actually trying to come up with models to make these, even if it means the 1D. I mean, you can even improving the speed of the 1D models. Can we come up with ways to improve the speed of the 1D models? That's possible. I think actually there's some low-hanging fruit in doing that. If Simo were here, he's got a lot of experience with this, but I think even using stretched grids, which have been problematic for pyrolysis, but should help. Yeah.
Okay, thanks.
Yeah, it seems like in the short term, the grid resolution issue or the discretization issue is going to outweigh any other savings. I mean, the need to resolve these solids. But
oh yeah, I mean, even you need a lot of grid resolution right now to get the transient correct.
And that was going to be my question. Coming from a finite element background, but do you have a sense of people are going to try to push this down to just a couple of cells across the solid if they test it out, and do you have a sense of what is a minimum resolution needed to get something appropriate?
Yeah, I mean, I think you should probably have 4 to 10 cells probably if you want something reasonable. So that's prohibitive right now.
Yeah. And then I had kind of a technical question on how you assemble the surfaces. You showed the HT3D surface type. Like on that beam example, have you applied that to multiple surfaces, or do you just specify it on one surface?
In that beam example, it's all around the I-beam. It's just on that I-beam
Other
obstacle.
than the patch, yeah.
Okay.
Okay.
Which one were you talking about?
Well, it had a constant temperature patch, and then the rest of
that was just a verification case. And in that case, it was adiabatic and then a constant temperature patch for the boundary conditions.
Gotcha.
Yeah.
And then does it automatically handle touching obstructions? Is that how, does it handle the heat flux between?
Yeah, so an obstruction, if you could have an obstruction that's HT3D, touching an obstruction that's not, right? And then that's an adiabatic condition as far as the solver is concerned.
Right, but if it touches another HT3D, then
it goes straight through. And in fact, if you want layers, you have to explicitly, right now, right? If you have a layer of insulation, a layer of this, a layer of that, then you make those different obstruction with different material.
Right, because the material is on the obstruction for the HT3D case.
Well, for pyrolysis, it actually the obstruction accepts a surf ID in which the surf ID has a material ID, because all of the kinetics is all still tied on the surf ID, it's still tied to the surf ID, and changing all of that machinery doesn't make sense. So there are two ways to specify material properties for an obst. You can, if it's just heat conduction through a metal, you can say material ID equals steel or whatever. If you have or you could say surf ID equals steel, and you could have a surf ID that had steel without a thickness and say, material ID equals this, and then you say HT3D equals. This is all described in the guides,
Sure.
the details of those. So.
All right,
and there are
thanks.
examples. So.
Other questions?
So I noticed you were talking about the deformation of the surface, like as it's maybe melting or decreasing or something in thickness.
Right.
Would you also be able to deform the obstruction itself and like translate, the top of the beam down one cell and the bottom of the beam down one cell, and kind of change the shape of it over time as it yields?
I mean, would we? It's possible, but we don't right now. So we don't into mess yet. So things shrink because all we've tapped into so far is burn away. So theoretically, like the heat flux would work as things are into messing and expanding. Okay, but then when you needed a new cell to deal with that, we don't have that like generation of a new obstruction there yet.
Right.
Yeah, we haven't dealt with that problem yet.
And the way you're handling the deformation is kind of more implicit anyway, right? You're not really deforming the cells themselves. So.
Right. I mean, these deflections were not, I think that I've seen anyway in the lab, have not been like massive deflections until you get to failure. So what Chow really wanted, he was just arguing to look over the course of an hour when we're heating this thing up. He wants basically a thermal boundary condition to put into his finite element solver. And he says that those values are going to be different if you're only considering normal conduction in FDS. So that's where this all started, really.
Right. Yeah, you don't want to recreate ANSYS. You just want to
Just give it better boundary conditions. That's the idea there. Yeah.
All right. Any other questions from the audience? All right. I guess that takes us to lunch. Thanks, Randy.